Hello and welcome, Professor Rasmussen, Chapter 4, a continuation of visual attention. So in the prior talk, I discussed selective attention in respect to inattentional blindness, change blindness, and attentional blink. In this talk, I'm going to go over some of the other components of visual attention, primarily components dealing with what are our eyes doing while we're scanning an environment, as well as what in the environment actually kind of captures our attention, or where does our brain push our attention. So those are going to be some of the things that I talk about in this lecture right here. Okay, so in respect to visual attention, we definitely have overt attention. Overt attention is where you're directing your conscious attention. So right now, I'm looking at my hat that is on my desk. Okay, now I'm looking at the computer screen. Okay, that's my overt attention. Now, in overt attention, your eyes are going to bounce from one location to another location to another location, so on and so forth. So what is the term for when your eye lands on a location, and then what is the term for when your eye is moving to another location but yet hasn't landed on that location that you want to look at? Well, the first thing is a fixation. The fixation is what your eyes are doing when they're looking at a particular spot. So a fixation is a short pause, often between the milliseconds of maybe 100 milliseconds to 500 milliseconds, depending on what you're looking at. When you're reading, it's probably around 200 milliseconds, give or take 50 on each word. So these are short pauses on points of interest while you're scanning a scene, and so that's a fixation. Now, the interesting thing is, even when you are fixated on, a particular letter or a particular person's nose or something like that, your eye is actually going to move a little bit as well. You might fixate a little bit over to the right or to the left, but just in general, even if you're keeping your eye extremely still, the eye is still likely going to move a little bit. This is called ocular drift. Ocular drift is this notion, or rather this topic, this concept, to describe the slight imperceivable movements of the eye that an individual is doing while they're trying to look at something. The interesting thing is, researchers still don't necessarily know why the eyes continue to move. It's possible that the eyes need to move to continue to get new information into the eye, so that it can focus properly. But there's many hypotheses that have been posed. All right, let's continue on. So a saccade is a nice word. Saccade. A saccade is when an individual is scanning a scene and they're jumping from one point to another point. So in between fixations, you're going to have saccades. So a saccade is a rapid movement of the eyes. It happens very quickly. It can happen within a couple hundred milliseconds, so very quick reaction time for this. From one place to another. Okay, so this is rapid movement of the eyes from one place to another. So it's in between a fixation and another fixation. They're very short in duration. Oftentimes they're only 20 milliseconds to 120 milliseconds. They're a very short period of time. That's because the eyes move very quickly. Now, this is a saccade. Okay, so there you have it. So we do these all the time, and how do researchers measure these? Well, they use eye trackers, okay, eye tracking device. So now, back in the day, the eye tracking devices were pretty poor. I mean, they're good, but they were pretty crude in respect to, you had to be in a laboratory. Oftentimes, there was a massive computer. There was these big goggles. Maybe it wasn't even goggles. Maybe it was just a computer screen that had a camera on it that was detecting where you looked, so on and so forth. But now, I mean, you basically can go out in the environment with a little pair of glasses on, and you have an eye tracker on, and maybe some sort of battery pack. Not so much a battery pack, but a image processing device that maybe either be large or small, that maybe have to fit in your pocket. So the eye tracker basically consists of some sort of camera. Okay, so number two, there's a camera, so it's recording what you're looking at. Then there's this sort of, possibly for at least this variety, there's some sort of illuminators that is going to help create the image where your eye is actually looking. You're not going to see these illuminators. You might see them, but you won't see the illumination of them necessarily. It's not going to influence your vision per se. And the camera is going to track where your eye is looking. So what's going to be able to happen then is, through 5 and 6, it's going to be able to put what you're looking. All right, so it's going to take from number 2, what you're looking, and it's going to combine that with where your eyes are actually focused, and it'll be able to paint a nice image, is that when you're looking at a scene, it'll know exactly where you're looking at in that scene, because of your eye movements. So let's try this out really quickly, okay? So just check out this scene, okay? And so this is an advertisement. I'm showing this because I love Ben and Jerry's. And you know what? Even more than that, I am a huge Grateful Dead fan. And I love Jerry Garcia. So how can I love Jerry Garcia? The only one I would like more is fish food. Oh, if you want to get an A in the class, just bring me fish food and do all your work. Okay, so where do people look at the most? Well, research, I don't know if this is legit research. I found this on a website. But it's likely true that this is where individuals look. So this is the heat map variety. A heat map is going to show you in respect to basically, just like a weather satellite, where there's a lot of red, where there's, orange, yellow. That's going to be an area of high intensity. Okay, storms are high intensity, a lot of precipitation, so on and so forth. But this is going to be an area where people spend a lot of time looking. And lo and behold, that's, probably where I looked, okay? That's probably where you looked. You probably didn't read, all those little things. You probably didn't spend too much time looking at the grass. You probably spent your time looking there. Now here's another one, okay? Okay, so where are you looking here? All right, keep it clean. Here's another one. So majority of, well, maybe even men and women, depending on their, your sexual attraction, are probably looking right there, okay, to the woman's backside, possibly her shoe, okay, what does it say, the retone, and then probably that logo down there, maybe that little chihuahua a little bit. Hopefully they're not looking at the chihuahua's butt, but there you have it, okay. So again, heat tracking, or sorry, a heat map with eye tracking, okay, showing where people look. So kind of important for advertisements, because if you're creating an ad, you don't want to have your object be the shoe and nobody looks at the shoe, okay. This advertisement is probably pretty effective because it captures some attention initially with the girl's butt. Guys or girls are probably going to look and be like, oh my gosh, that's someone's butt right there. Hard not to look at it. And then you kind of start moving around, maybe to the retone, maybe to the dog, and then you look at the shoe because it's a shoe ad, so on and so forth. So interesting work in respect to marketing and advertising. All right, so let's go to the last one here. This is going to be not so much in a heat map, but just primarily in respect to the fixations and the saccades. So if you're looking at this advertisement, I couldn't find the actual original. So if anyone can find the original, this Escape the Winter from the Royal Tours, some sort of, I don't know what it is. I can't really read that. My computer screen's really dim. But anyhow, an airline or some sort of cruise ship, email it to me, or you can't bring it to me in person, but bring it in electronically or something, because I want to be able to use this as well. I couldn't find it though, with like a 10-minute quick search. But this is where people look, according to this eye tracking data. These are oftentimes what's demonstrated here is the lines are from fixation to fixation. Okay, so I think the first fixation was on escape towards the end there, and then you can go to the second, the third, so on and so forth. What indicates here how long a person spent on a particular location is the size of the circle. So the larger the circle, the longer the time a person spent looking at that particular location. Smaller the circle, obviously the smaller amount of time, shorter duration. So the interesting thing is there's also what's known as saccadic suppression or saccadic masking. Now this is an interesting phenomenon that researchers have found, that during a saccade, the brain blocks/suppresses visual motion from awareness. So it is as though you're not perceiving and recognizing any sort of new information while your eyes are moving. Now that's kind of interesting, right? So when your eyes are moving from fixation to fixation, there's no new information that is entering your consciousness. It still may influence your brain in some way. However, you're not aware of what is changing, what is happening in the scene from fixation 1 to fixation 2. Okay? Now the interesting thing is that this suppression is strongest at about 75 milliseconds prior to a saccade. So our brain obviously is controlling when our eyes move, and the brain knows before the eyes are going to move, because the brain is controlling the eye movements and you're controlling, the brain, or the brain is controlling you, whichever one you want to think about it. This is a philosophy class. But nonetheless, it happens typically around 75 milliseconds prior to the beginning of a saccade. And then this suppression starts to reduce as the saccade terminates. Okay? So that's saccadic expression, saccadic masking. So essentially, what researchers have found is that if a change in a change detection task happens during a saccade, would a participant be able to recognize the change? So if a change occurs during two fixations, so during a saccade, would the person be able to detect the change? No, exactly, and that's what researchers have found. So change blindness occurs during saccades. Again, supporting the notion that during a saccade, we are not aware of the visual information. Sensory memory is holding that information over. However, we're not aware of the actual that environment during any changes in that environment during the saccade. Okay, so here's just some more scenes. I want you to just to watch them or just to view them, just one here, and pay attention to where your eyes go. Oh, isn't that beautiful? Okay, so where did your eyes go? So oftentimes they're going to go to areas of high contrast, possibly bright lights, color differences. These are going to be items in the environment, in a location, in a scene. They're going to pull your attention. So this is an important thing to note, that items in an environment, they pull your attention. Okay, so colors, blinking lights, moving objects, definitely they're going to pull your attention. That's why you see kids oftentimes look at bright objects. They're going to look at high contrast toys. They're going to look at objects or people that are moving, okay, not too fast, but just in a pattern that they can actually perceive it. So this is pulling the attention. So here's probably some locations that an individual looked, maybe the doorway, maybe back in there because there's some contrast, probably this whole massive scene right there. I mean, I'd probably circle the whole house, and then probably the Christmas tree, maybe even the chimney, but most people don't look down here too much, down where these little shrubs are in the snow. Up in the sky, it's kind of, dark. I mean, it's a super pretty picture. I mean, oh my God, could you imagine just pulling up to this house? Beautiful, right? I mean, you don't even need to celebrate Christmas to know that this is gorgeous. um, but yeah, so, these are the areas that an individual would look, and those are oftentimes the areas that, like I said, high contrast, colors, lights, so on and so forth. If the snowman started moving, your eyes would definitely go to that, and that would be kind of freaky. All right, so let's keep going on. So now here's another one. All right, look at this scene, and just enjoy it. Think about where your eyes go. All right. So where did you find yourself looking? How about in this scene here? Where did you look? Well, actually, let's go all the way back to the first one. So how about this one? Where did your eyes look? Well, they probably looked all over, right? Stapler, maybe the lamp. Holy crap, there's a rat, right? Yeah, so your eyes probably definitely were pulled to the rat. How about this nice, gorgeous kitchen scene? Oh my God, there's a gasoline can in the back. What's going on in that house? Right? Boom, gasoline can. Okay. Looking in. Oh, look at that cute little. What the heck's a dumbbell doing in there? Dumbbell on the toilet. Okay, so I don't know. Maybe you looked at these. Maybe you didn't. You probably looked at a lot of these objects. But did anybody have their attention pulled to any of these objects? Yeah, hopefully, right? So this is the environment mixed with your brain that is pulling your attention to these objects. So atypical objects have been found by Vo and Henderson, 1999, and a whole host of others as being something in the environment that can pull one's attention. Okay, it doesn't necessarily. Sorry. Your attention is pushed. I keep saying pull. Maybe I don't know if I keep saying pull, but I say pushed. Your attention is pushed to these objects. Sorry, I said pull earlier, but your attention is being pushed to these objects, not because the object is flashing, not because the object is colorful or high contrast. It's because your brain is pushing your attention to that object because that object is atypical. It doesn't belong in the scene. So the reason that your vision is being pushed to this object is that you have what's known as a scene schema. So a scene schema is a stereotype of a scene. So scene schemas consist of this as an example. What do you typically find in a bathroom? Well, probably some soap, maybe a toy, a towel. You probably don't find a dumbbell. So if you see a dumbbell, your attention's going to be pushed to it, okay, because it typically is not located within a scene. Same with the kitchen. All those things are totally normal, okay, totally typical. However, you see a gasoline can, you better believe that is not typical to a scene, to to a kitchen, all right? So therefore your attention is going to be pushed to it. Same with the rat in that other scene, okay? So basically these scene schemas help guide our fixations from one area to another, and oftentimes what researchers find is that individuals will fixate longer on a area that has an atypical object. Some researchers have found that people will fixate on these earlier than areas, participants will fixate on areas where there's an atypical object earlier, but that's not always necessarily found. Typically, people will fixate on the atypical objects more and for longer duration than the typical objects. Alright, so again, that's pushing your attention to an object or a scene. So in respect to these fixations, how long, how do you do this when you're naturally interacting in an environment? So if you have to give it instructions to, make PB&J, well, here's going to be the fixations, this is CODS, so on and so forth. So typically what researchers find is that the eyes go to the area, sorry about that, I'm just going to ignore that. Sorry about that, that was my phone ringing. So the eyes go to an area that will assist in completing a task. Okay, so that makes sense, right? So if you need to, make the PB&J, your eyes are going to go to where you need to, utilize these objects. So the eye fixation precedes the movement by about a second. So this is kind of interesting. So wherever you're going to move, your eyes typically start to fixate there, or at least start to make the saccade towards that region about a second before the movement initiates. Okay? So this is one thing that researchers have found. So this may help us interact with the environment quite smoothly. So if we fixate on a location before we actually make a movement, then we can know, oh, that's where the object is located. Boom, we fixate on it, and now we can start moving towards that object. So it's a nice coupling between vision and action. So let's talk really quickly about where your eyes are and covert and overt attention. So wherever our eyes are, our attention is as well, right? So if you think about a police officer or special, some sort of special Secret Service, that's what I wanted to say. So the Secret Service, they wear those sunglasses. Sometimes police officers are looking at you, but is their attention always just on you? No, it could be kind of, covertly applied to another location. So people try to be sneaky. Same with sports, right? You're pretending to pass it one way because you're looking that way, and then you make some sort of blind pass. And not blind, you know what's over there because your attention is kind of covertly placed in another location. Okay, so this is some evidence of that. Maybe we have this covert attention. So covert attention, the ability to not necessarily place your eyes on that location, but to know what's going on in a separate location without putting your specific eyes, on that object. So to direct attention in a secret / hidden manner, do we have that ability? So here's some research that looked at this. This is called pre-cueing. I believe there's going to be a COG lab on this. So this is cool stuff, but I'm going to give you a little example right off the bat. This is posed by Posner and colleagues in the 70s. And so what I'm going to have you do is I want you to keep your eyes fixated on the X. Okay, it's actually a plus mark. So on the plus mark, when you see the box, so a box is going to pop up, just tap your leg. Okay, tap your leg if the box is on the left, and tap your right leg. So tap your left leg with your left finger if the box is on the left. Tap your right leg with your right finger if the box appears on the right side. Okay, but you always have to look at the plus mark. You can't look away from it. All right. So there's also going to be an arrow that may help you in predicting when and where the box arrives. Okay. All right. So let's get started on pre-cueing. Remember, looking at the plus mark. Okay, so, easy task or difficult task? Pretty simple, right? I mean, all you gotta do is look at the plus mark, and you either have to go left or right. Now, sometimes you notice that the arrow was correct, right? So the arrow was a valid trial where the arrow was pointed to the right, and the box appeared on the right. Some of them were an invalid trial where the arrow was pointed to the right, but the box was on the left. Now, this is what it looks like. So, oops, I went back. Don't want to go back. So, when the arrow is pointing to the right, box appears on the right. Arrow pointing to the left, box appears on the right. That would be an invalid trial. So, which were easier? Well, it was probably the valid trial was easier. But did you make any mistakes? Probably not, but you might have. And the mistakes you probably made were on the invalid trials. So when researchers do this task, there's many more valid trials than there are invalid trials. So then the participants obviously start to believe the arrow because the arrow is there to help and speed up reaction times. So what is the dependent variable here? Well, the dependent variable is think about it. So what's the dependent variable? What's the independent variable as well? So the dependent variable is reaction time to answering. Okay, it also could be accuracy as well, but mainly reaction time. How long does it take an individual to say that the box is on the right versus the left? Now, secondly, the independent variable would be whether it was a valid or whether it was an invalid trial. Okay, so here's the CogLab data. I don't want to go over it. I'm going to go over this in class, and that's some old data. But yeah, so that's basically what the pre-queuing is all about. And here's the actual data from what researchers have found, Posner and colleagues. So in the valid versus the invalid, the reaction time is the dependent variable. What you see is in the invalid trials, it takes the individual considerably longer, not a long time, I mean it's only 50 milliseconds, but 50 milliseconds, this is going to be a significant difference, suggesting that the difference between those two means, the valid versus invalid, was not likely caused by chance. It was likely caused by, that difference between them was caused by the invalid actually taking longer than the valid. So this is interesting work that has been generated by pre-queuing. So what does this suggest? Well, it suggests a couple things. First of all, attention can be diverted to another area even when you're not looking at that area. How do we know that? Because you're looking at the plus mark, and then when that arrow is going to an area where you're actually going to have where that box is going to appear, the person's going to be quicker than if there was no arrow. So if there's no arrow, the person is quicker when the arrow is pointed to it. The person is also much quicker when the arrow is pointing the opposite way. Okay, so a person does get tricked by this, or a person can get helped by this. Okay, so this would almost be like in the environment. If you're expecting, a pass to come from the left, and you're looking straight on, and now you're kind of, covertly paying attention from the left to the left side, thinking that that's where you're going to attack. Well, you're quicker to react if it's in fact true. Now, if it goes the opposite way, you may actually be slowed down a little bit. So this can definitely come into play upon the football field or possibly some other sports too, even like baseball. Alright, now one thing that researchers have found, eagerly, suggests that possibly it's not so much an object, that it is not so much a location where an individual is gathering their pre-queuing from. It may be an object that actually can pre-queue them. This is just data I'm throwing in here. But nonetheless, this does look like we do have the ability to have covert attention. So the overt attention is looking at something. Sometimes we don't detect a change, just like we said earlier. Covert attention, not looking at something, but attention is directed to that location. This can assist with detecting changes. But again, change blindness, inattentional blindness, these things can always happen. So just really quickly, just to wrap things up here, this is just one final comparison between what we're talking about in this talk and what we talked about in the prior talk, just to wrap up this visual attention. Think about change blindness. Remember in the change blindness task when you have the mud splash, the interruption, the blank screen, the mask? What does that represent in the real world? So what we're talking about here is from the original scene, the original image displayed for 100 milliseconds, going to the blank screen, almost displayed for a second, and then to the test display, displayed until the participant figures out which one or answers which object changed. That blank screen, that blank display, what does that serve as? What does that represent in reality? Does it represent anything, or is it just some sort of weird artifact that is in these change blindness experiments that make change blindness and change detection occur? Or rather, a failure to detect change occur. Right. It's real. It's something that we really do. We just talked about it earlier. It's a saccade. During the saccade, our eyes don't necessarily, or rather our brain is not aware of what's actually changed in the environment. And also, to couple that though, not only do we have multiple saccades potentially every second, we also blink at least one every 5 seconds. sometimes even quicker, sometimes less as well. So interesting work here where that actual blank display does map onto things in the actual environment. So there is some sort of potential external validity, some reason why these blank displays are useful and can be incorporated into these change detection tasks. Ladies and gentlemen, that's a wrap up for this visual attention. I hope you understand fixation versus saccade, how pre-cueing, how overt, covert attention can be researched, as well as what objects in the environment pull our attention, as well as how our brain pushes our attention to various locations within a scene. Thanks for tuning in, and make sure you tune into the last one where I'm going to talk about where is attention. It's almost like where in the world is Carmen Sandiego? I don't know if you ever played that before, but this is where in the brain is attention. Tried to make something funny out of it, but I couldn't. Alright, thanks.